today, we're going to learn about how to describe motion. So the description of motion is sometimes called kinematics. So the description of motion, and it's called kinematics. Okay. So just like I talked about in the last class, we're going to do this in a few different ways and try to translate between one and the other. Translate between a native language like English to mathematics to pictures to plots. We'll be doing all of those things. So the basic starting point is to describe something called the position. All right? And to make life easier, we're going to start by assuming the motion is along a line. So it's one-dimensional. All right? So we'll start with one-dimensional motion. So we'll use a symbol, and the symbol I'm going to use is for position, is the first thing we need to know. And the symbol I'm going to use is S. Now, S can be positive or negative. All right? And already I'm going to use some kind of plot. Here's a graph. I have to define an origin. All right? So this is my origin. If S is on this side of the origin, we say it's positive. If S is on that side, we say it's negative. So we have fundamental starting point. Where is the object? Okay? And position is the starting point. Next, we need to know about velocity. So what is velocity? Well, velocity is the rate of change of position. In English, you would say rate of change of position. And we might write that as V equals delta S over delta T. Okay, just like that. So we've already used some English. We've used a mathematical formula, V equals delta S over delta T. All right? And then we want to use some other words. Delta S is called displacement. It's not position. It's the change in position. It's how much the particle has changed over some time. All right? Delta T is sometimes called duration, right? Or change in time. So now we know the velocity of the particle is delta S over delta T. All right? Now, we also know a few other things. Sometimes we're interested in the velocity at a very specific time, and sometimes we're interested in the average velocity over some finite amount of time. All right? So instantaneous velocity at a specific time is equal to, we say V is equal to ds dt. Okay? In other words, it's the derivative of s with respect to time. All right? Whereas the average velocity and we put a bar on top to indicate average, is really delta S over delta T. All right? So it turns out that the average velocity becomes the instantaneous velocity if you make delta T small enough. All right? Now, one of the things you should know from calculus is what the derivative represents on a graph. All right? So if I have a graph of position versus time, and it looks something like that, how do I see the velocity on that graph? Well, if I want the velocity at this point, it's given by the derivative. And the derivative is the slope. All right, so the velocity is the slope of the tangent line. Tangent to the curve. To the S versus T curve. That is what equals V. All right, so the velocity is that. All right, if we wanted the average velocity, we would just take 2 points on this curve, let's say there and there, draw a line between them, and we take delta S over delta T. All right, average velocities are usually not quite as useful as instantaneous velocity. And now I'm going to make a distinction that we don't usually think about in regular ordinary English. And the distinction is between the word velocity and the word speed. All right? So velocity is V. Speed is equal to the magnitude of velocity. All right? So that's the magnitude. That's how fast you're moving. All right? So in physics, technical language, speed is not the same as velocity. Velocity in one dimension could be positive or negative. Speed is always positive. Now, we have another way of visualizing velocity. And that way is called a motion diagram. All right. So imagine you have a car. Now, I know none of you, or almost none of you, have ever even driven a car. But maybe your parents have, or maybe you've driven a motorcycle. All right? And like many cars, especially older ones, it leaks oil. And let's say this oil lets out a drop every so many seconds. So there's a drop, another drop, another drop. All right? Then if we look on the floor, on the ground, we will see a bunch of dots. All right? So let's say we see this. All right? So between each dot, we have delta T is a constant. All right, so that's your diagram. And let's say you started this way. So you're moving this way. All right? Now let's say later on, the car still has dropping oil, but instead of this diagram, you see this diagram. So the question is, which diagram shows the car moving faster? Is it the top one or the bottom one? Well, to answer that, you notice the displacement here is smaller than here, but delta T is the same for both. So since the displacement is bigger here, we see that the velocity for this time is bigger, at least in magnitude. The speed is bigger here than here. All right? So if I call this V1 and V2, then I can say V2 is greater than V1. All right? So that's called a motion diagram. These are very useful in the sense that, let's say we have some motion and we want to describe it, and we have a camera, all right, or a video projector. We video it. So every frame, we see the same object, but it's moved a little bit. So one frame after the other. So the time between frames is equal, but the object has moved. If we then superimpose all those frames and put a dot at the center of the object, we will get a motion dot. So now we have position, we have velocity. The next most important quantity is acceleration. So what is acceleration? Well, acceleration we get in the same way as we got velocity. Acceleration is the change in velocity with respect to time. All right, so the definitions are exactly the same. We write A is equal, the average A is delta V over delta T, and the instantaneous A is the derivative of V with respect to T. All right, and then obviously, since V is already a derivative, we can write the acceleration as the second derivative with respect to T. Okay, so this is acceleration. And if you recall from the first class, this is the key quantity because forces, interactions, cause acceleration. And then that acceleration then leads to the velocity changing. Just like with position versus time, we can have velocity versus time, and we can have a curve like that. All right, so we can ask the question, what is the acceleration at various places? And to get that, we simply look at the slope at various places. So for instance, right over here, the slope is 0. So that means the acceleration over there is 0. Over here, it also looks 0. Here, the velocity is increasing, so the acceleration is positive. Notice the acceleration is positive here and here. So even though the velocity is negative, the acceleration could be positive. All right? And then if I had this come down again like this, then the acceleration would be negative here. So A is less than 0 here, A equals 0 there, A is greater than 0 there, and right there, A equals 0 again. All right? So we can ask, what's going on with the particle? Well, what's happening is the particle starts moving to the left because it has a negative velocity. It's not, that velocity is more or less constant, not changing much. And then suddenly the velocity speeds up, and then the velocity is slowing down a little bit. Okay? It's still increasing. No, the velocity is not slowing down. It's still increasing until it gets to this point. And at that point, it stops increasing, and then the velocity starts to decrease. All right? It's still positive, but it's slower. It's moving slower. So there are a few rules that you can, I don't know if you need to memorize them, but you can get from all these results. V is greater than 0 and speeding up. So that's like over here. Then that means A is greater than 0. If V is less than 0 and speeding up. So that means the velocity is getting more and more negative. So A is less than 0. Okay? All right, and if V is greater than 0 and slowing down, that means A is less than 0. So even though the velocity is positive, the acceleration is negative. And then you could do if V is less than 0 and slowing down, then A is greater than 0. Okay. And again, we can show all this with a motion diagram. So let's do a motion diagram for a car going from one stop sign, one stoplight to another. And we'll say the other one is red. Right, so it has to come to a stop. All right, so you're at one intersection here, and you're just sitting there for time. So it's hard to indicate sitting there, but you might do it by having a bunch of dots like that. All right, and then eventually the light turns, and you speed up. So that's speeding up. And then you stay at a constant rate for a while. All right, and then you see the red light, and you have to slow down. All right, so then you slow down and eventually come to a stop. So here A is positive. When constant velocity A is 0, and here A is negative. So A greater than 0, A equals 0, A less than 0. So here V is greater than 0, V is greater than 0, V is greater than 0. Okay? So that's one way of describing motion using a motion diagram as well as the others. All right. So I'm going to end today's class with a typical concept or error that many students used to make. I don't know if they make it as anymore because teachers probably just tell you the answer. All right? So the idea is the following. I throw this piece of chalk up in the air, and I ask what happens at the very top when the chalk is right there at the top. What is its position, velocity, acceleration? Well, its position at the top would be wherever it is relative to the ground. All right, so I throw a ball up. So it's going up. You know, it starts out, it has some velocity, but it's slowing down. All right, so it's right there. All right, so this position we'll call y equals h. And right there, the velocity is 0 because it's come to a stop. It's slowed down. The velocity is 0. Question is, what is the acceleration up there? Now, if you ask the man on the street or the woman on the street what the acceleration is there, and they probably don't even know what it means, but most likely, most people, most students even, would say the acceleration is 0. Is that correct? Is the acceleration 0? Well, let's imagine it was 0 there. So if the acceleration is 0 at this point, and the velocity was 0 there, that means its velocity would not change. And then we'd have this very odd situation that when I threw the chalk up, it just stayed there, stuck, as if the air was holding it in place at the top. That obviously is not true. So the acceleration is not 0 at the top of the orbit. In fact, the acceleration is less than 0. A is less than 0. Partly, you can see that from the motion diagram. All right, it's slowing down, so the acceleration has to be negative. All right, it's going in the positive direction if we call up positive. Acceleration being negative means it's slowing down. And in fact, on the surface of the Earth, if you ignore air friction, the acceleration, which has the value 9.8 meters per second squared, is constant, more or less constant on the surface of the Earth, very close to being constant. All right, so we see that position, velocity, acceleration are 3 distinct concepts, and we have to be able to talk about each one separately.